Hi students, and welcome to this week's first video. This week's going to be about Chapter 15, Nuclear Magnetic Resonance Spectroscopy. In this chapter, we're going to be learning about a powerful technique for determining the structure of organic molecules, in particular when combined with infrared spectroscopy and perhaps mass spectra. In particular, the mass spectra are useful for determining the molecular mass of the compound. We can determine the structures of many different organic compounds using this combination of techniques. Now in the lab, we're going to be doing a lot of practical aspects of reading spectra and determining what structure they correspond to, and that's going to be most of what you're going to work on for practice this week. The book is going to cover many theoretical aspects which will help you to remember basically a lot of the data. And for example, here you see this thing called ppm. Certain hydrogen atoms here will, when you do a nuclear magnetic resonance spectra, will have a certain so-called chemical shift in ppm. And these will be things that you're going to have to memorize when you're preparing for the ACS exam. But you don't have to memorize them in isolation. It's better to understand where they come from. And these videos will explain a lot of that to you, which is something that I will not have time to cover in the lab alone. But we'll do a lot of practice and we'll do a lot of discussion given these chemical shifts. And you'll get a lot of the theory behind why these chemical shifts are the way they are based on these lectures. So first, let's define what nuclear magnetic resonance spectroscopy is. It's probably the most powerful technique that is used currently for determination of structures of organic molecules. Not only can it tell you something about the functional groups that are present in the molecule, which IR is even better for, but it can tell you information about which atom is bonded to which other atom, which gives you much more structural information than an infrared spectrum usually can. The way NMR operates is it involves an interaction between electromagnetic radiation and the nucleus of an atom. And we're going to talk about exactly how that occurs. We're going to focus on carbon and hydrogen nuclei. There is NMR that's done for other nuclei, but these are not the most commonly done, therefore kind of more specific types of applications. In particular, the information we're going to want to get is the connectivity between the molecules, which atoms are bonded to which other atoms. And NMR provides a lot of information about that. So protons and neutrons in a nucleus behave as if they are spinning. They have a quantum mechanical property called spin. Now, it's not exactly spin in the sense that it's spinning around like a sphere would or something like that, or like a top would. But the result is similar, and that's why it's called spin. So when you have a spinning electrical charge, you will have a magnetic field generated around that spinning or moving electrical charge. And that is going to be the same with protons. And so if an atom has an even number of protons, this effect will not be observed since their spins will essentially cancel one another out. But if an atom has an odd number of protons or neutrons, it will have a net nuclear spin. And so examples of isotopes that have that include hydrogen-1 with simply a single proton, carbon-13, which would have 6 protons and 7 neutrons, nitrogen-15, fluorine-19, and phosphorus-31. Again, we're going to be focusing mainly on hydrogen-1, also called proton NMR, and carbon-13. The spinning charge in the nucleus, the so-called spinning charge, creates a magnetic field. So if you have a charged body here that is rotating, then and a magnetic field will be produced orthogonal to that, or perpendicular here. So we have the spinning of this electrical charge here that induces a magnetic moment perpendicular to this spin, and it's similar to if you have a bar magnet. There's a magnetic field generated from the north and the south of the bar magnet around, and these lines represent the magnetic field, which weakens as you get further and further away in distance. So normally what you'll have in no magnetic field, when you have just a proton or some atom is that that spinning can occur, that so-called spinning, producing the magnetic field can occur in any direction. And so if you're just holding a normal sample of hydrogen or carbon, you'll not observe any magnetic properties because the magnetic fields will be all canceling each other out because they're all distributed completely evenly in all directions. However, if you expose these nuclei with odd numbers of neutrons and or protons to an external magnetic field, you will get situations where you have a magnetic field aligned with the external magnetic field or opposed to the external magnetic field. We call those that are aligned, we call them alpha, and we call those that are opposed, we call them beta. And so basically by exposing them to this magnetic field, it's kind of like the North and the South Pole. We're going to have a spin aligned with the magnetic field or opposed to that magnetic field. And so they will no longer be disordered in this way. When this occurs, you have two separate states for the nuclei, or the so-called alpha state, in which the magnetic field is aligned with the external magnetic field, and this is a lower energy state. And then you have the beta spin state, which is opposed to the external magnetic field and has a higher in energy. And there's a certain difference in energy here for each of these nuclei, and that difference in energy is going to depend on its local environment in the molecule. And so what we can do is, once we've established these spin states by exposing a chemical sample to a external magnetic field, we can then have it absorb a particular frequency of radiation. And this energy difference tends to be in the energy of radio waves, so a relatively low energy compared to infrared spectroscopy, which involves exposure of the sample to higher energy infrared light, or visible spectroscopy, where the same way our eyes operate, which is even higher energy light. This is low energy radio frequency light. And so what we can do is when the nucleus with the alpha spin state is exposed to radio waves that just have exactly the right energy, the right frequency, and thus the right energy. Remember from GChem that energy, in the context here of a electromagnetic wave, energy is directly proportional to the frequency, which is indicated with this nu here. Higher frequency means higher energy, and this is a very small proportionality constant. This is just a constant that we don't really have to pay much attention to. Basically, though, for energy for these radio wave photons, if they have just the right frequency, they'll have just the right energy to reverse the spin state from alpha to beta and absorb that light. And we can then use a detector to determine what energy of radio waves were observed. The stronger the magnetic field, the greater the energy gap will be. And each proton or carbon-13 nucleus will have a different exposure to the external magnetic field depending on its local environment in the molecule, and that will give us a lot of information about that local environment. So the external magnetic field will cause the electrons to circulate and oppose the magnetic field. This is referred to as diamagnetism. So the nuclei actually experience less of a magnetic field than the bare nuclei would, because they're shielded by the electrons. And this is what I referred to as the local environment. So the most shielding that the nucleus experiences from local electrons, the smaller the magnetic field, and thus the smaller the energy gap will be. The smaller this delta E will be. So nuclei that are surrounded by less electron density will be said to be de-shielded. And so they will experience a greater magnetic field, and thus they will require a higher energy of radio frequency waves to flip the spin state. So the amount of, that's just what I said here, the amount of radio wave energy necessary for the alpha to beta energy transition depends on the electronic environment. So when the energy absorbed here, we say that the atoms are said to be in resonance and the term resonance is different from when we're talking about resonance in electrons like we did in chapter 2 of the book. This means that basically they they've been flipped in spin state. It's a different use of the term resonance. Unfortunately, the same word, but a different term here. So the amount of energy required for each proton or carbon-13 nucleus to spin flip tells us about its electronic environment, and so we can know more about the structure. So that said, NMR devices can operate on different magnetic fields. Generally, a stronger magnetic field will give us better spectra in which the peaks are easier to separate or to see apart. We say that it will have higher resolution. And so better NMR spectrometers have higher magnetic field strengths. And magnetic field strengths are measured in a unit called Tesla. And so we have certain, the kind of early days nuclear magnetic resonance spectrometers, and the one that we have in our lab, which is a newer one, but is a smaller desktop version, operate at about a 1.41 Tesla magnetic field. The newer and higher powered NMR machines than the ones you might encounter when you go to a big university later on, like UCR or somewhere else, tend to operate on a magnetic field of 7 or sometimes even higher Tesla. And the result is that you have a greater energy to separate the spin states. And so what that means is that it will, depending on which type of spectrometer that you use, you will be exposing the nuclei in the sample to a different radio frequency energy in order to achieve the flipping of the spin state. And so when it comes to NMR spectroscopy and the results, the spectra that come out, we actually don't want to measure the absorption in terms of the exact frequency, because then we would get different frequencies for machines that operate at different magnetic and different external magnetic field strengths. The magnetic field itself can be generated in a variety of ways. Generally, it's when a high current is passed through a superconducting material, so this is held at 4 Kelvin. Now that said, you might notice we have one in our lab that is not held at 4 Kelvin. It's held at room temperature, and that's because there have been new superconducting materials that have come out in recent years that allow for superconduction to occur at higher temperatures, but not at the kind of field strengths that we might want sometimes. So the one at UCR is probably cooled to 4 Kelvin and can operate at a greater magnetic field strength. So the greater the current, the greater the magnetic field. Practically speaking, what is used in these is a pulse Fourier transform spectrometer. And this is as opposed to scanning a wide variety of radio frequencies over a period of time, a pulse Fourier transform type instrument will shoot a short burst of all frequencies of radiomagnetic radiation, and then use a mathematical technique called the Fourier transform in order to convert that to absorptions at various different frequencies. So this can be done much more quickly than scanning over a series of frequencies. So each of the atoms that is then exposed to this radio frequency radiation will get excited, absorb this radio frequency radiation, and then relax, emitting energy. And when this energy is emitted, it is going to be detected by a detector, and then the ultimate absorption will be determined by what's called a free induction decay, meaning that and not to go into too much technical detail, but as the nucleus spins, it turns around and around like this, like a top that you're spinning, and slowly it will align again with the external magnetic field, and that's the free induction decay that is measured. So the free induction decay contains all the information for each atom. It's converted using a mathematical technique called Fourier transform, which I won't go into, but you may learn about in your higher level mathematics classes. Indeed, the infrared spectrometer works on the same technique. It will emit all the infrared light at once, and then use a Fourier transfer to show what was absorbed at what different frequency. So these FIDs, many of them will be taken and averaged together to get a better and better signal-to-noise ratio, a peak that has basically a very flat baseline and a very easy-to-see peak. Before analysis, the NMR samples were prepared. Usually, they'll be diluted in a deuterated solvent, and the reason why a deuterated solvent will be used is because, and deuterated meaning instead of hydrogen, it has deuterium, which has one proton and one neutron, and this is because the deuterium, because it has an even number of combined protons and neutrons, will not undergo this process, right? The magnetic spins will cancel each other out. Remember that in order for this to work, we have to have an odd number of protons and neutrons. So that way, the deuterated solvent will not give NMR signal. So we can just focus on the signal of our sample. The sample will be usually spun at a high rate inside the magnetic field to average any variations that occur within the instrument in any particular direction. So, for example, here we have a deuterated solvent, deuterated trichloromethane, common deuterated solvent, and we have lots of different deuterated solvents with different polarities to dissolve various different samples. So the sample itself, although the internals of the instrument are cooled by liquid helium, the sample itself will generally be held at room temperature. The sample will spin inside this large instrument, and that will average out any distortions in the magnetic field. The radio frequency pulse will be sent in from the instrument, and then the detector will send back a signal, and the Fourier transform will be done. So here's what an NMR spectrum looks like. So you can see here that on the bottom is a quantity called chemical shift, and the chemical shift we'll talk about it in a little bit. But the chemical shift is a useful way of showing the absorption, that the radio frequency light that is absorbed, because it's going to be independent of the external magnetic field strength. So no matter which NMR instrument you're using, the chemical shift will be the same. And the NMR spectrum will contain several pieces of information that we'll want to analyze. One will be how many independent signals that we have. One will be the chemical shift, which is a measurement of the energy of the radio frequency light that was absorbed, which tells us about the local magnetic environment of each hydrogen 1 or carbon 13 atom. The signal intensity will tell us how many protons or how many carbon 13 nuclei are represented by this peak. And then the signal shape, you'll notice that many of these peaks here have very interesting patterns. Like this one has a larger peak in the middle with two smaller peaks almost the same height on either side. This one has two smaller peaks on either side and two almost equal height peaks in the middle. And then this one has a complicated set of peaks here. And so the splitting pattern, the way that the peaks are arranged within each large peak here, can tell us something about the structure of the molecule as well. So when we take the NMR signal, we're going to have some of the protons that are going to be in very, very similar or essentially identical magnetic field environments. And we're going to call those protons chemically equivalent. And they can fall into two large categories that are described as homotopic or enantiotopic. In homotopic protons, the molecule has an axis of rotational symmetry, and it allows one proton to be rotated into the other without changing the molecule. So these below are examples of homotopic protons. And what this means here is, we can see here, if we rotate along the vertical axis here, we rotate this molecule, we have no difference in the molecule. And so these two protons here would be considered to be homotopic. Here we have a rotation in the plane of the page. If we rotate this around this central axis here, we rotate it around, the molecule will be identical after the 180-degree rotation. So these protons are also homotopic. Finally, again, we have a rotational plane in the plane of the page here. If we rotate this 180 degrees, along this vertical rotational axis here, we will get the same molecule. So these are homotopic protons. These would give both together the same signal in the same spot. Another way that you can test for homotopic protons is to replace the protons one at a time with the other atom and see, is this the same compound or not? So if we replace the protons with, for example, deuterium, which is represented by a D here, or with anything really, we see that in fact, so if we replace this, with a D, we can simply say, well, if we rotate this, we get the same molecule. So if we replace this one with a deuterium and leave this one alone, that would give us this structure. If we replace this one with a deuterium and leave the other one alone, that would give us this structure. But these are exactly the same compound. I can tell because if I take this one and I flip it like a pancake vertically, I get the other one. So if the resulting compounds are identical by replacing one hydrogen and then the other, what you've got is homotopic. So it can sometimes be difficult to see this rotational symmetry. So that's one way that you can test it without having to visually rotate the molecule so much. The other types of chemically equivalent protons are those that are enantiotopic. If the molecule has a plane of reflection, it will make one proton the mirror image of the other. And so this would be if you have a proton that if you replace it, you will get one enantiomer, and there will be another enantiomer as well. And so essentially you will have the mirror image of one another. So and these are both examples of enantiotopic ones. If I replace one with the other and I get the mirror image, it will be the same molecule here. Let me show you how that test will work. You can test this. Let's say we replace this hydrogen atom with deuterium. Then we get if we replace this one here with the deuterium, then we get the structure that's on the left here. If we replace the other atom with deuterium, we get the structure that's on the right. But these are enantiomers of one another. I can tell because if I have a mirror plane here, this is the exact mirror image. The deuterium here is in the same plane, closest to the mirror. The hydrogen is in the same plane here, furthest from the mirror, and then the chlorine and the fluorine are in their same positions as well. So since these are mirror images of one another, they're enantiomers, and we would say that these hydrogens are enantiotopic. They're equivalent, chemically equivalent. And so these are going to give one signal, a larger signal because it will represent two protons, but one signal in the NMR. So if you want to determine if the protons are equivalent, one way is to look for rotational symmetry. If you can find a rotational axis that when you rotate it 180 degrees, you get the same molecule, then the two hydrogens there that you would be looking at, or any of the hydrogens there you're looking at, will be homotopic. If there's a mirror plane, if you replace one and you get the mirror image and it's the same, then we say it's enantiotopic. But if you have neither rotational symmetry or a plane of symmetry within the molecule, or a mirror plane equivalence, then the protons will not be chemically equivalent. So for example, here, these two hydrogens are not chemically equivalent. If you replace this hydrogen with a deuterium, you get this molecule right here. If you replace this hydrogen with deuterium, you get this molecule right here. Now, the quick way to spot this is if you see these are not mirror images of one another, right? The deuterium here is these would be mirror images if these two were switched, the OH and the H right here. You can see that this is not mirror image right here. The quick way to spot this is if you have a chiral carbon somewhere in the molecule, then the two hydrogens here are not going to produce an enantiomer if you replace them with something else. They're going to produce a diastereomer. Two molecules that are differing in terms of their 3D arrangement of atoms, but are not mirror images of one another. Okay. And so these protons here are not chemically equivalent, these two protons. So they will give you two separate NMR signals. So if the protons are neither homotopic nor enantiotopic, they're not chemically equivalent. So I think it's a lot easier to see it on the standard projection rather than the Fisher projection. But you should be aware of what Fisher projections look like. We briefly reviewed that previously, and we'll go into more detail later when we talk about carbohydrates. But basically here, these two protons are not going to be enantiotopic or homotopic. They're not going to be chemically equivalent because there's another carbon here that has that is chiral. We can tell it's chiral because it's attached to 4 different things, right? This right here, this methyl group on the left is different from the ethyl group on the right, which is different from the hydroxyl group on the wedge, and is different from the hydrogen on the dash. There's no rotational or reflectional symmetry here. So these hydrogens are not homotopic, they're not enantiotopic, they're not chemically equivalent. So this can all be very difficult to do. You saw we had to either like look for this plane of rotational symmetry or this plane of symmetry within the molecule. That can be difficult to do. Very simply, the way to know if two protons or some protons are going to be chemically equivalent or not is to actually apply these particular shortcuts. This is the way I generally do it. I don't usually think of enantiotopic or homotopic. I look for these types of patterns here. First of all, 2 protons on a methyl group will be equivalent if there are no chiral centers in the molecule. So as you saw, this molecule on the last slide had a chiral center to it, and that made it so that these 2 protons here would not be chemically equivalent. That would not be the case if we have something like this. Right now, here we actually have a plane of symmetry in the molecule. We also have rotational symmetry, and so these hydrogens would be chemically equivalent. But in the left example, they're not due to this chiral carbon. So just very quickly, let's see if there are any chiral centers in the molecule. Then 2 geminal protons will no longer be chemically equivalent. The 2 protons on the CH2 group will not be equivalent if there are chiral centers in the molecule. So here we can see that this molecule has no chiral centers. All of these carbons are sp2 hybridized, so they cannot be attached to 3 different things, 4 different groups rather. They're only attached to 3. These have 2 hydrogens, so these carbons are not chiral. And so there are no chiral centers, meaning that these 2 protons and these ones as well, these will be chemically equivalent, and then these protons here are chemically equivalent as well, due to the reflection, the rotational symmetry here along this rotational axis. But as soon as we introduce here a chiral carbon, this carbon being chiral because it's attached to 4 different groups, at this point now, these protons are no longer chemically equivalent. They are diastereooptic. They're not chemically equivalent. They're not diastereotopic, rather. They're not enantiotopic or homotopic. Here's another shortcut that you can use. The 3 protons on a methyl group will always be equivalent to each other. So that's a very great and easy shortcut to use. If you see 3 protons on a methyl group, they're chemically equivalent, period. You don't have to think anything about rotational symmetry or anything like that, or reflectional symmetry. Finally, multiple protons are equivalent if they can be interchanged either through a rotational or a mirror plane. So here we have, and this got cut off a little bit here, but here we have a mirror plane in the molecule right down this oxygen. We also have a rotational plane too. So these protons here are all equivalent. So these protons will be equivalent because of the rotational and the mirror plane. And then these protons here, there are 3 of them, these will be equivalent along with these ones here because they're all attached to the same methyl group. And then, so these are all equivalent because they're all attached to the same carbon, 3 on the same carbon. That's this one right here. And then these ones will be chemically equivalent to these ones due to the rotational symmetry. Now, you may recall that there are various conformers, for example, the chair structure in cyclohexane, where the hydrogens are in different environments due to their position. So you may remember that in cyclohexanes, we'll have 6 axial protons and 6 equatorial protons, which have very different local electron environments due to their relative positions. These hydrogens being pointing away from the ring, far away from all the other carbon atoms. The axial ones being much closer to the other. For example, all these red hydrogen atoms are much closer to each other than the blue ones. And so they have different electronic environments, but we only see one signal for all 12 of these in cyclohexane. And the reason is because remember that the cyclohexane rapidly interconverts between 2 chair formations, and the axial hydrogens become, or the axial groups become equatorial, and the equatorial groups become axial upon a chair flip. And this chair flip happens in a much faster time scale, at room temperature anyway, than the operation of the NMR spectrometer. And so the result is that these are all seen as equivalent protons, even though at any given one given time they are not in the same electronic environment. They're interconverting between axial and equatorial so quickly that they are effectively in the same environment on the time scale of the NMR spectrometer. This chair interconversion rapidly, the NMR is too slow for this. If you reduce the temperature, you will slow down this chair flip, and then the protons will begin to appear as not chemically equivalent protons. But at the normal operating temperatures of NMR, they will all be equivalent, and conformers will interchange much quicker than the operation of spectrometers. So we don't have to worry about different conformers usually. They're spinning and moving around in a way that's much faster than the operation of the NMR itself. So in terms of determining this so-called property of chemical shift, as I said, you're going to get an observed shift in hertz in the frequency. Basically, this is going to be the frequency that is absorbed to achieve the spin flip in the molecule. But this is going to differ, as we said, depending on the external magnetic field. And we don't want to have different values for this shift that differ from instrument to instrument to instrument. Also, we need to have a relative 0 point, something that we compare the frequency to. And most commonly, a small amount of trimethylsilane, which is this molecule here, is introduced into the sample to give an internal standard or a 0 chemical shift. And all chemical shift, or the frequency absorbed, is going to be measured relative to this trimethylsilane. Now, the reason why trimethylsilane is used is because silicon has a lower electronegativity than carbon. And so what's going to happen is that the carbon is going to pull electron density towards itself here. And that's going to provide more shielding or more electron density for the protons that are attached to the carbon. And what that means is that due to the greater shielding, each of these protons will experience a lower magnetic field, and thus will absorb a lower frequency of light. And so we can compare all the other protons. They should absorb a greater frequency of light unless they're in some relatively unusual type of electronic environment. And so the way we calculate the chemical shift is we determine the radio frequency that is absorbed in the instrument, which again will be larger for higher magnetic field instruments, and we divide that by the operating frequency of the instrument. And so when we had the 1.41 Tesla magnet, this usually operates on, or generally absorbs frequencies of RF radiation of about 60 megahertz or million hertz. Whereas if we have the around 7 Tesla instrument, that will absorb radio frequency at a higher frequency around 300 megahertz. And so if, for example, we have benzene, which has 6 equivalent protons, and we measure the absorbed frequency on a 300 megahertz instrument with a 7 Tesla magnetic field, that frequency absorbed will be about 2,181 hertz. And then we'll divide that by the operating frequency of the instrument, which is 300 million hertz, or 300 megahertz. And so we get a chemical shift of 7.27 times 10 to the minus 6. Now, times 10 to the minus 6 is the same as 1 divided by a million. That's 10 to the minus 6. So we call that parts per million. So we call the 10 to the minus 6, we call that parts per million. And so that gives us a nice round number for our chemical shifts, which end up being like, this would be 7.27 parts per million, which is the way we express these. And then these, because they're divided by the frequency of the instrument, and these the frequency absorbed and the frequency of the instrument are directly proportional to one another, we'll have the same chemical shifts no matter whether you were using a 60 megahertz instrument or a 300 megahertz instrument. So for example, if we do benzene on a 60 megahertz instrument, the absorption will be 6 times smaller. Instead of being 2,181, it will be 6 times smaller, and it will be about 436. But we'll divide, or 5 times smaller rather, because we're going to have a 5 times smaller frequency. 60 is 5 times smaller than 300. So this is 5 times smaller, but we have a 5 times smaller operating frequency. And so we get the same chemical shift, which is 7.27 times 10 to the minus 6, or 7.27 ppm. And so although the hertz of the signal is different in the different instruments, the chemical shift, which is indicated by this lowercase delta, relative to trimethylsilane, is constant. So here, the shift for the proton signal is calculated as a comparison to that observed for trimethylsilane. So we have the observed shift of trimethylsilane, and we're going to call that 0. Then everything's going to be relative to that. So trimethylsilane is the chemical shift itself is a dimensionless number, because it's going to be hertz, which is frequencies per second, divided by hertz, and so those are going to cancel, and we get no dimension to this unit. And we give them in parts per million again, because that makes for an easier number. Instead of saying 10 to the minus 6, we just say parts per million. And most proton NMR signals are going to occur between 0 and 10 parts per million. So as I was mentioning before, when NMR spectroscopy was first coming out, what would happen is they would use a constant energy, and then they would operate over a range of magnetic field strengths. And so some terminology came about due to that. When we said there was a low field strength here, and a certain amount of light was absorbed, at a higher field strength, that would be a higher amount of light. But for the lower field strength, we said we called it downfield meaning lower field strength, lower magnetic field strength. These tend to correspond to larger chemical shifts, because they are a larger energy, so they achieve that particular transition at the lower field strength. Remember, the higher field strength will require a larger energy transition. And so if the absorption is occurring at a lower field strength, then that means that it was a higher energy transition. But if the same transition is occurring at a higher field strength, it must have been you had to increase that field strength, to increase that energy to be equal to the ones downfield. And so we call this upfield at a high field strength. And notice an interesting thing about the numbers of chemical shift is we have larger numbers going left, which is unusual for graphs, but they're done in this way as a kind of historical artifact due to the fact that they scaled from low field strength up to higher field strength in the past. And so these peaks came out left to right in this way as they scaled from lower to higher field strength. And so we continue to have the peaks that are higher chemical shift be on the left and the ones that are lower chemical shift be on the right. The shielded protons require a stronger external magnetic field to be excited, but those would have a lower chemical shift because they have greater shielding. So current NMRs, though, are different, but we still have this historical artifact about the way we lay out NMRs because people have just become used to reading them in this fashion, from higher field strength to lower field, from lower field strength to higher field strength. But the lower field strength corresponds to a higher energy absorption, so a higher chemical shift, less shielding over on the left. There's greater shielding on the right. We get lower chemical shift due to lower exposure of the nucleus to the magnetic field. In terms of chemical shift, the chemical shift is going to be greater the more de-shielded the proton is, the more electron density has been removed away. And this electron density removal can happen in a couple of main ways. The first of these can be due to the inductive effect, which we learned about in Chem 212. This is when you have a highly electronegative atom. This will pull electron density away from the atom it's attached to, and also to the atom that atom is attached to. And so we can see by having a very, very electronegative, so if we have no electronegative atoms attached, like in methyl, the protons on methyl will have a chemical shift of approximately 1 ppm. They will be shielded somewhat due to the electron density of the carbon and the hydrogens here. But if we attach a very electronegative atom like fluorine, that's going to pull electron density away from the carbon, but there will be, and so that's just a direct effect of having these two atoms bonded. But then there will be an inductive effect where the electron density is pulled away from each of these hydrogens in this direction, thus de-shielding them. And thus they will get a greater exposure to the external magnetic field, and thus it will take a greater amount of energy in order to induce the spin flip. And so you will get a greater chemical shift of approximately 4.3 ppm in this case. The more electronegative atom the atom is, the greater the chemical shift will be induced. So here, fluorine being the most electronegative at the top right of the periodic table, chlorine being next among the halogens, bromine being next among the halogens, and iodine here being the least electronegative among the halogens. In addition, this effect will be magnified if we have a greater number of halogen atoms attached. So for one chlorine atom, as you saw here, that's going to result in these 3 red protons giving a signal at 3.1 ppm. If we have 2 chlorines, that will be 5.3 ppm. If we have 3, that will be 7.3 ppm. Now, it's important to note that this effect, this inductive effect, falls off very quickly as we move further and further away from the electronegative atom. So it's strongest for the hydrogens that are attached to the alpha carbon, or the carbon directly attached to the electronegative atom. It's reduced for the hydrogens attached to the beta carbon, that's 1 carbon away from the electronegative atom. So you can see that chemical shift is only 1.6 ppm here in the chloropropane. Finally, once you get to the 3rd carbon away, the inductive effect is completely gone. And we can see that this behaves the same basically as a methyl atom. It's a little bit lower due to the fact that there's extra carbon atoms here donating a little bit more electron density to shield the hydrogens a little bit more than when there's only 1 carbon atom. So that's one reason why protons here will give a higher ppm signal, is due to the inductive effect of being attached to a carbon that is either directly attached to a electronegative atom or 1 carbon away from the carbon attached to an electronegative atom. Now, shielding will increase if there is a greater number of carbon atoms attached to the alpha carbon here. So for a methyl group that's attached to another carbon atom here, this carbon will donate a little bit of electron density and will shield these hydrogens a tiny bit. If you have two carbon atoms here attached, now there's going to be more donation of electron density. It's going to be shared a little bit equally, a little bit from these carbon atoms to the other one. And so there will be a little bit more shielding on the hydrogens. Finally, if we have three carbon atoms attached, there's even more sharing of this electron density, and this hydrogen ends up being even a little bit I said that the wrong way. They'll be sharing in this direction, so there'll be here a little bit less shielding, and we'll have a greater ppm. I've got that reversed in my head here. So these carbon atoms here are sharing electron density with this carbon atom. Even though they're not more electronegative than carbon, they are taking away a little bit of this electron density. And so there's a little bit less shielding for these hydrogen atoms. That's even more the case when there's three carbon atoms. There's going to be, even though the carbon atoms all have the same electron density, they're pulling it a little bit away here. And so we get a little bit of de-shielding for this proton. And thus it's de-shielded a little bit, and it has a little bit higher of chemical shift. So we can use the chemical shifts to figure out whether the hydrogen is attached to a carbon with 1, 2, or 3 carbons attached to it. Again, sorry for the mistake. There is a de-shielding effect that occurs because these carbon atoms are sharing electron density with this one, and thus removing it a little bit from the hydrogen. In terms of other neighboring functional groups, oxygen is extremely electronegative. And so when it is attached to a carbon, it's going to have a large inductive effect. Not quite as big as fluorine, but quite significant. And so you saw with fluorine, just going back to fluorine here, you saw that the difference in the inductive effect here between having no fluorines and having one, well, this difference here was 4.3 ppm minus 1.0 ppm. And so it was a difference of about 3.3 ppm due to the inductive effect of having a fluorine atom. For oxygen atom, it's quite big too, because oxygen is quite electronegative. It's the second most electronegative atom relative to fluorine. And so it has an inductive effect where it decreases shielding on the protons here, and thus increases the chemical shift for these by 2.5 ppm. And so what we can do is, if we have a general idea of these relative amounts of de-shielding that occur and the resulting chemical shift, then we can add these together to get the overall chemical shift. So we have an alcohol group attached to a carbon that's attached to one other carbon, which is called a methylene group. On the methylene group, we're going to get 1.2 ppm of shielding. And that's just going right here, this carbon atom attached to two other carbon atoms. And then we add to that the de-shielding effect of the inductive effect of the oxygen, which gives us another 2 ppm of chemical shift, for a total of 3.7 ppm. If we have an oxygen that's a part of an ester group, that electron density will be even further shared here due to resonance and pulled towards this oxygen atom, will lead to an even greater de-shielding effect, resulting in an additional 3 ppm here of chemical shift. So we add the 1.2 ppm again due to this carbon atom being attached to two other atoms, but add on the effect of the ester oxygens, which is 3 ppm, for a total of 4.2 ppm. And you can see that this gives us a pretty accurate estimate of the actual chemical shift of these protons. The actual chemical shift is 3.7 here, identical to what we would predict. And here it is slightly less, 4.1 instead of 4.2. And so this gives us a good way of estimating what the chemical shift would be in various environments for different protons on a molecule. When it comes to a carbonyl group that is on a carbon, on the beta carbon here, so we call this the alpha carbon for these protons, a beta carbon. We have a carbonyl group on the beta carbon. That's going to have an inductive effect of 1.0 ppm chemical shift. And again, we have the methylene group, this carbon attached to two other carbons, giving us 1.2 ppm, or a total of 2.4 ppm or 2.2 ppm chemical shift. The actual chemical shift in this molecule here is 2.4, And so that's a pretty good estimation of that as well. Now that we've discussed the inductive effect, there's one more effect that there will be on the chemical shift, and that's due to the so-called anisotropic effects. And given that this video has gone on pretty long, I'm going to stop there, and I'm going to start the second video next time. And so we'll then discuss the second aspect of the molecular structure that affects the chemical shift. I will say now that if you have pi bonds that are close by to the hydrogen that you're looking at and determining the chemical shift, those are going to provide additional shielding due to a magnetic field that they generate due to their movements of electrons, and due to the resonance in the pi bonds, or the sharing of these electrons. They move around more. They generate a magnetic field, and that will also that will end up shielding, deshielding these protons due to this induced magnetic field. And we'll discuss that in the next video.